Right, welcome to my channel. Today we'll be talking about impact, impulse, and momentum. That's linear momentum. Alright, let's have a brief chat on this before we dive into derivation of formulas, proving, and then solving examples. Now, suppose two blocks of mass m and capital letter M, where m is greater than m, were to collide. According to Newton's third law of motion, which states that to every action there is equal and opposite reaction. Alright, all this will be discussed properly in this course. However, since the mass are not equal, the response to this force, that is the change in their velocity, will be different. Let me just give a real life illustration. If a car collides with a human being, there are different level of injury that can happen to the person or even to the car. Now, the first case I just want to say is if the car is moving at a very low speed, the impact it's going to have on the person, it will be different compared to the car moving at a high speed. I believe we can relate with that. So you see that the force and the impact on the person actually is totally dependent on the speed and the mass of the car. So that's what impact is all about. Now, Newton describes the quantity of motion as the product of the mass of the object and its velocity. So you see, the phase quantity of motion is actually called the linear momentum. So mathematically, we represent linear momentum with letter P, and note that it's a vector quantity, and then mass times velocity. Velocity also is a vector quantity. So it means that the momentum is actually in the same direction with the velocity, and the force that will be applied is also in the same direction. Momentum is a vector quantity, and then it's very important we know the units. All right, the unit for mass is kg, the unit for velocity is meter per second. All right, so the unit for linear momentum is kilogram meter per second. All right, we have a question here. We are asked to prove that force times the change in time equal to the change in momentum. Right, to prove this, the very first thing we need to do is to actually consider Newton's second law of motion. And Newton's second law of motion mathematically can be expressed as, right, the sum of all force equal mass times acceleration. So I'm going to title this one as equation 2. All right, now the sum of all force is actually what we call the net force, and it's actually a vector quantity. So let me indicate it here. The sum of force is a net force, and it's a vector quantity. All right, so the net force is responsible for changing the velocity of the object. It's actually that which is responsible for changing the velocity of an object. So quickly, I'm going to just write the expression for acceleration here. We all know that acceleration is the change in velocity, the rate of change in velocity. That's velocity, change in velocity over change in time. I'll title this one as equation 3. Okay, so now substituting equation 3 in equation 2, it becomes F equal mass times change in velocity over change in time. I'll title this equation 4. Right. I think it's already looking like what we know. If we take a good look at equation 1, we see that momentum, that's this place, is actually mass times velocity, and we can see this expression in equation 4. So I can say equation 4 now is F equal m change in V over change in T equal m change in V. It's actually the momentum. I'll put the change here, or better still, let me simplify it like this. This becomes change in mv over change in T. Right, so mv is actually the momentum, so I'll write change in P over change in T. Looking at this and this, that's F equal change in P over change in T over 1. If I cross multiply, it means F change in T equals change in P. This actually proves that the force times the change in time equal linear momentum. And we're going to discuss more in details concerning the left hand side, because this expression here is what we call impulse. Right, I can further expand, I can expand this. If we talking about change in momentum, it means that there at one point there is an initial momentum and there is a final momentum. So I can say F change in T equal change in mv. Note that m is a constant, so I can say m change in v. It means that there is a variation of velocity. So we have the final velocity, we have the initial velocity. So I can say F change in T equal m Vf minus Vi. This signifies the final velocity minus the initial velocity. Right, let's solve a question that relates with what we are doing. Okay, a body of mass 2 kg moving vertically upwards as its velocity increase uniformly from 10 meters per second to 40 meters per second in 4 seconds. Neglecting air resistance, calculate the upward vertical force acting on the body. And then we're given that acceleration due to gravity is equal to 10 meters per second. All right, to solve this question and not to get confused, it's very, very important we bring out our parameters. Every details are given to us in the question. Okay, so the mass of the body, equal 2 kg. The initial velocity, that's Vi, equal 10 meters per second. The final velocity, Vf, equal 40 meters per second. And then lastly, the time, T, equal 4 seconds. and there is no need for converting anything. Everything in their standard units. So straight away I'm going to write the formula. That's from this point. This formula is what we're going to be using. So F equal M VF minus VI over T equal to 40 minus 10 over 4. So it's equal to 2 times 30 over 4 equal 60 over 4 equal 15 Newton. So that's all about the introduction. Let's dig deeper. Okay.